Welcome guys. Welcome guys. So today let's keep solving some interesting mathematical question. Yeah, so this is my new series that I will up every week or every 3 to 4 days, and I will upload some interesting mathematical question which is not related to the analysis or something, just some difficult high school question. And hope you guys enjoy. If you're not a mathematical, if you're not like the so pro or some very abstract mathematical, we are giving some brain teaser. Basically, you guys can have fun. Okay, so before I start, please subscribe to my channel and click the like button and leave a comment. Okay. You can leave the however you like. Okay. So the first one is that find a polynomial p of x such that p of z satisfy p of 0 equals 0 and such that p of x squared plus 1 equals p of x squared plus 1. Okay, and the second one is that find a px such that the p of 0 is 0 and satisfy these two. Okay, so usually this type of problem it's not easy to get solved, right? Because somehow like you only have like this so-called functional equation. So it's not like that somebody give you p of 1 equals to 1 and p of 2 equals to 2 and p of 3 equals to 3 or something, and you can solve, which you can just directly use the Lagrange point, the Lagrange polynomial or something, just find the roots, right? So it's not guaranteed that you can do this. Okay, but there's a very powerful tool that I want to mention to solve this type of problem. So let's see there's a very powerful tool. So there's a powerful result that suppose you have a polynomial with degree n, and you get p of x1 equals to, and you also know some points. Basically, they are all different. Basically, you got all different x1 up to xn plus 1, and you know that px1 equals to px2 up to px3 up to pxn plus 1, which is the same number called c. Then you can guarantee that p of x equals to c. So reason is that usually for the fundamental theorem of algebra, right? For the degree p polynomial, if it's degree n, then you should only have the n roots, right? But but now you have n plus 1 number which give the same number, right? So you can, if you want to prove it, you can define f to be, let's say p of x minus c, and then you can prove that. So you can see that f x1 up to x n plus 1 is 0. Right, which give you that the f must be identically equal to be 0. Right, so this is a very powerful tool that you can use to prove that there are only prove in this case there's only p of x equal to c, so is the only answer. Right, so we need to use this powerful tool to deal with these two equations. Okay, and hopefully we can find. Okay, so maybe we see the first one says that first one is p of 0 equals 0. And p of x squared plus 1 equals to p of x squared plus 1. Right, so from this one, we know that the p of 1 equals to p of 0 squared plus 1, which is 1. Right? And so now we get p of 0 is 0, p of 1 equals to 1. Right? So it give us some hint that if I were you, I would guess p of x equals to x. Right? This is what I guess. Right? But I hope to prove that this is the only one. Okay. And so from here, I get what? I get p1 squared plus 1 equals to what? Equals to p of 1 squared plus 1, right? So this is p of 2 equals to 2. Oh, right. So now we already have 3 of them, right? Which is 3 of them. So we are hopefully really close, right? And we keep going, right? I get p2 to the square plus 1 equals to p of 2 square plus 1. So it's 4 plus 1, so which is 5. Oh, so we get p of 5 equals to 5. And then we keep going, we get 5 squared plus 1 equals to p of 5 squared plus 1, which is 26. And this guy is 26. So p of 26 equals to 26. Okay, so now you see the proof is done, right? Because if you keep going, then you get infinite n, so you get infinite integers such that p of n equals to n. right? So the first one is 0, 1, 2, 2, 0, 1, 2, 5, 26, and then the next thing you get should be 26 squared plus 1 equals to 26 squared plus 1. And you keep going, so you will get infinite integers such that P of n equals to n, right? So, but from this principle, we know that this is a finite degree polynomial. So finally, from this, we guarantee that P of x must be equal to x. And the proof is that I can define g of x to be P of x minus x. And from these infinite integers, I always get g of n equal to 0. So we get infinite n. So from this principle, we are guaranteed that the only solution for this question is P of x equals x. So this guy is x. Okay. Okay, so we solve this. How now we can solve second one? Let me just write down. So second one satisfies the P of 0 is 0, and the P of x equals a half. P of x minus 1, P of x plus 1. Okay, so I don't know what you guys think, right? But what I think is that what I want to guess is that I would guess P of x is some constant times x, right? And let's try. So P of 0 is 0, right? And P of x is ax, and P of x minus 1 plus P of x plus 1 will be ax minus 1 plus ax plus 1. So will be 2ax, and there's a half, right? So I would guess this is correct, right? But the idea is that we hope to prove that this is correct. This is the only one. Okay, so it's the same reason that let's see. So let's see what's P of 1, right? So P of 1 is a half. Okay, so right, so we got 0. Right, so we got P of 2 is 2P of 1, and then we did not get anything. Okay, so okay. How about P of 3? P of 3 will be half P of 2 plus P of 4. And so it looks like we still oh, by the way, this is too fast. So I plot x equals to 1, right? I get this. How about x equals to 2? I get P of 2 equals a half P of 1 plus P of 3. And the P of 1 is what? I don't know P of 1, right? But I know what? I know, so this tells you 2P of 2 is P of 1 plus P of 3. Right, so from here, I get P of 2 is 2P of 1. So which I get P of 3 is 3P of 1. Okay? So the key idea is that we hope to show P of n equals to nP of 1 for all n. Okay? For all n which is an integer. And it's easy to show this, right? We can do the mathematical induction. So let's say, so n equals to 1 is trivial. And let's assume that n equals to k. So actually, I can assume that n equals to 1, 2 up to k. Satisfy the P of k equals to n P of 1. And obviously that the n of so now I can check for n equals to k plus 1. So P k plus 1 equals a half P of let's say what, k minus 1 k plus maybe let's do this, right? So okay, so maybe let's see. So I already assume that n from 1 to k satisfy the P of k equals to nP of 1. Now we want to prove that P of k plus 1, right? So I can go P of k will be half pk minus 1 plus pk plus 1, right? And these two are in our assumption. So this is a k minus 1 P of 1. This is a k P of 1. So from here you get pk plus 1 is k plus 1 P of 1. Okay, so we prove this. So now everything is done, right? So let's write down the final proof. So we know what? We know P of n is n P of 1, right? So let's define P of 1 to be some number, let's say a. So we get P of n is na, right? So I can define a polynomial g of x defined to be P of x minus ax. And then we know that g of x contains every integer, right? So let's say g of x is 0 for all x belongs to integer, right? But the p of x defined to be a polynomial, right? So g is a polynomial, and g have more than n roots, right? Basically, g have infinite roots, which is 0. So g is identically 0. So which tell you that p of x is defined must be ax. Okay, so this is the powerful tool that I provide in this video, and two very curious quick examples to tell you that what's this powerful tool is actually really powerful. Okay, check you. Hope you guys subscribe to my channel. Thanks. Bye.